Hello everyone, this is Colin from Fiber Optics for Sale. In this video, I will explain what is fiber optics, so let's get started. From its name, we know that fiber optics is composed of fiber and optics. Here, fiber is a very thin plastic or glass strand. Optics means light. So fiber optics basically means light that travels in a strand of plastic or glass fiber. This picture shows a bunch of fiber enclosed in a single black color protective jacket. So how is light guided and travels inside the fiber? This video shows a beam of light that travels inside a water stream by total internal reflection. Optical fibers work the same way, so let's take a look. The previous video gives us a basic idea of how light would travel inside a fiber. Now let's see what a glass fiber is composed of. A glass fiber has a cylindrical structure and is composed of 3 layers. At the center is a core. Core has higher refractive index. Outside of core is the cladding layer. Cladding layer has lower refractive index than the core. The third layer is a plastic buffer coating. This buffer coating layer doesn't affect the fiber's optical performance. It is there for mechanical protection only. The right picture shows how light is coupled into the fiber's core and bounced back and forth in the core and travels along the fiber. The core and cladding layers are all based on fused silica, which is a type of glass. But this fused silica is extremely clear, with almost no impurities. This transparency is extremely important, so that the light can travel for a very long distance, such as hundreds of kilometers with minimum loss. This makes trans-Pacific and transcontinent fiber optic communications possible. Here comes the question, why doesn't the light leak out of the fiber? That is why we have to explain the phenomenon of total internal reflection. The left picture shows Snell's law, which guides how light travels at the interface of the core and cladding. The core has a higher refract index, n equals 1.5. The cladding has a lower refract index, n equals 1.4. When light incidents at the interface between the core and the cladding at different angles, some power is reflected back, and some power enters into the cladding, which is refracted. But when we increase the incident angle to greater than a critical angle theta c, no more light enters into the cladding. All light is reflected back into the core. This phenomenon is called total internal reflection. The important point here is the critical angle theta c. If light enters the fiber less than theta c, it will quickly leak out of the fiber and won't travel long. When the light enters the core at an angle greater than theta c, it will be bounced back and forth at the interface of core and cladding and travels very long distance along the fiber with very low loss. This picture visually shows the total internal reflection process. The manufacturing of glass fiber goes through 2 steps. In the first step, a preform is made. This preform has exactly the same proportion of core and cladding material as final fiber product, but in a much bigger size. It looks like a thick glass rod, as shown in the bottom picture. Then the preform is hung at the top of fiber drawing tower. The tower is a couple stories tall, as shown in the right picture. The preform is heated by a furnace which softens the glass. The softened glass drips and is pulled downward by gravity. A diameter monitor carefully monitors the fiber's diameter, which usually is 125 micrometers. Then the coater deposits a layer of plastic buffer coating for mechanical protection, which usually is 250 micrometers in diameter. And finally, the fiber is winded onto a spool for storage and transportation. A basic fiber optic communication system must have at least 3 components. The light source, which usually is a laser. The laser is turned on and off quickly by a driving circuit. In this modulation process, the original electronic signal is translated into light signal. The second part is the fiber. The fiber's purpose is to transmit the light through a very long distance, such as from New York to Paris. And the third part is a photodetector. The photodetector detects the light and generates electronic current. In this process, it translates the light signal back into electronic signal. Of course, real-world systems are much more complicated, but this gives you a rough idea of how it works. This illustration shows the laser modulation process, which turns the laser on and off by an electronic signal. The laser generates stable, continuous light. The most common light colors or wavelengths are 850 nanometer, 1310 nanometer, 1550 nanometer, and more. The light itself is an electromagnetic wave and is called the carrier wave, as shown here. The top is the electronic signal, which has much lower frequency than the carrier wave itself. When this signal is used to turn the laser on and off, the bottom illustration shows a generated pulse, which is a low-frequency signal envelope modulated on top of the high-frequency carrier wave. The most common signal speeds include 100 megabit per second, 1 gigabit per second, 2.5 gigabit per second, 10 gigabit per second, 40 gig per second, and 100 gigabit per second. 100 gigabit per second is currently a state-of-the-art technology, and many fiber optic companies are working hard to commercialize it. Many people search on Google for the advantages of fiber over copper. Fiber's most important advantage is its almost unlimited bandwidth. The bad thing with copper is that the higher speed the signal, the larger loss it gets. As shown in this picture, in coaxial copper cable, the higher speed the signal, the higher its loss. So high-speed signal won't travel long on a copper cable. After just a short distance, maybe just a couple hundred meters, the signal becomes too weak to work. On the other hand, the loss of signal has no dependence of its speed in optical fiber. So for the same speed, light signals travel much longer in fiber than electronic signals travel on copper cable. This table lists the most common high-speed Ethernet standards. For 100 megabit per second, copper supports up to 100 meters, while fiber supports up to 40 kilometers. For gigabit Ethernet, copper supports still 100 meters, fiber supports 70 kilometers. For 10 gigabit Ethernet, copper is still 100 meters and fiber is 80 kilometers. Now you see the difference. The bottom picture shows the size comparison between a copper cable and an optical fiber. Both carries the same bandwidth. There is truly no match for fiber's bandwidth capabilities. In order to fully utilize the fiber's bandwidth, people are using WDM technologies to increase the bandwidth in tens of folds. WDM stands for Wavelength Division Multiplexer. What this means is that many different colors or wavelengths of light is put into a single fiber. This picture shows a simple 4-channel WDM, but there are 32 channels, 64 channels, or even more are available on the market now. Now imagine how many information can a single fiber carry. If each wavelength carries 40 gigabit per second signal, then a 10-channel WDM system can carry 400 gigabit per second. Not to mention a 100-channel WDM system. So there you have it. Please leave your comment below if you'd like to see other topics. Don't forget to visit foforsale.com for more free fiber optic tutorials. I will see you in the next video.